So today I want to look at some theorems about roots and polynomial equations. So first thing I want to do is let's consider these two equations here. These two equations are equivalent equations. That means they're the same equation, just written in different forms. This first one right here, this is written in standard form. And then the bottom one, it's the same equation, just written in factored form. And then over to the right here, I have the roots, which are also referred to as the zeros, or the solutions. Here's what I want you to notice. All these roots that I have are rational. That means they can be written as a fraction with integers. If we look at my roots here and the denominators are all 1 here. My leading coefficient on my equation is a 1. Now let's look at the numerators. The numerators, we got -2, 3, and 4. These are factors of 24, which is my last term. Alright, let's look down here at this other example that I have worked out here. Again, I have two equations that are equivalent. The first one, the 24x cubed minus 22x squared minus 5x plus 6 is equal to 0. That's written in standard form. The second one is the same equation, just written in factored form. And then over to the right, here I have the roots. And these roots, again, are all rational roots, because they can be written as fractions with integers. All right, so let's look for that pattern here. Let's look at the denominators. What do we have for the denominators? We got 2, 3, and 4. Well, 2, 3, and 4 are factors of 24, which is my leading coefficient. Just like we had in the first example, we had all 1s here. And those are factors of my leading coefficient here, which was a 1. Now let's look at the numerator. In the numerator, we got -1, 2, and 3. Well, these are factors of my last term when the equation is written in standard form, my constant term. This is always going to be the case. If you have a polynomial equation and it has rational roots, okay, your denominator here will always be factors of your leading coefficient. And your numerator will always be factors of your constant term. We'll talk more about this later on. But before we move on, I want to make sure you understand what it means to be a rational root. I want you to be able to look at some roots and tell me whether they're rational, irrational, or imaginary. So I have 4 examples of roots up here. To be rational, it means you can write it as a fraction using only integers. And if you forgot what integers are, well, there's 0, 1, 2, 3, and so forth. And they're opposites. So this is what integers are. So to be rational, that means you can write it as a fraction using only these numbers. That's what it means to be rational. All right, so let's look at A. I got 2i square root of 3. Well, this is a dead giveaway because it has I involved. Anytime it has I involved, it's going to be imaginary. Or we can refer to that as a complex root. Complex and imaginary root mean the same thing. So 2i squared root of 3, that's a complex root. Or if you want to, you can call that an imaginary root. All right, let's look at b. We got 2 over 3. Well, it's written as a fraction. 2 and 3 are integers. So b is a rational root. So this is a rational root. C, we get the square root of 5. What is the square root of 5? Well, I don't know. We plug it in the calculator, it'll give us a long decimal. Kind of like pi. It's a long decimal that doesn't end and there's no pattern to it. So it's like pi. So this is an irrational root. So anytime you have square roots that don't have a perfect square under it, it's a dead giveaway, that's going to be irrational. And then the last one, we got 2 plus the square root of 5. Well, 2 is an integer, and the square root of 5 is what we just saw on C. That's irrational. So when you take whenever you have an irrational number involved at all, as long as you don't have I involved, it's going to be irrational. So D is an irrational root as well. All right. So remember on that first screen, we had this. We saw this pattern. Okay, someone discovered this a long time ago, and I came up with this theorem. This theorem is called the rational root theorem. And it only deals with rational roots. So roots that can be written as a fraction using only integers. So roots like 2/3, 3/5, -4/5, -2/1. These are all rational. So here's what the theorem says. If P over Q is in the simplest form, and it's a rational root of a polynomial equation with integer coefficients, then P must be a factor of your constant term, just like we saw. If P must be a factor of your constant term. And Q must be a factor of your leading coefficient. We saw that on the first screen. Remember? Go back here. Our numerator, which is right here. Those are factors of my constant term. And then my denominator, those are factors of my leading coefficient. This is always the case. Let's write that out. So we got, all right. So if it's a rational root, it's going to be in this form here. We got P over Q. P are factors of your constant term. And then Q will be factors of your leading coefficient. This is what you want to remember. This is basically what this theorem says. I would write that down in your notes. P is factors of your constant term. Q is factors of your leading coefficient. That's only for rational roots. It doesn't. This theorem doesn't work for imaginary or irrational roots. Only rational roots. So roots that can be written as a fraction using only integers. All right, so let's look at an example here. We're going to use this rational root theorem to work this example out. It says find all the rational roots of this polynomial equation. X to the third plus x squared minus 3x minus 3 is equal to 0. So we want to find all the rational roots. So we're looking for rational roots, roots that can be written in the form P over Q. P, remember, is factors of your constant term. So it's going to be factors of what? What's my constant term in this equation? Negative 3. So it's going to be factors of negative 3 over factors of what? Factors of your leading coefficient. What's my leading coefficient on this equation? A 1. So let's list out all the factors of negative 3. Well, 1 divides negative 3, and so does negative 1. So we have positive and negative 1. 3 divides 3, and so does negative 3. So we have positive and negative 3. Are there any other integers that divide negative 3? No. So these are all the factors of negative 3. 1, negative 1. 3, negative 3. So there's 4 factors. What are all the factors of 1? Well, we got 1, right? And we also got negative 1. So what we can do is we can generate a list of possible rational roots. All right? So what we're going to do is we're going to generate a list of possible rational roots. We know it has to be in this form here. The only numbers, it's going to be a fraction. The only numbers that can be on top are 1 and 3. They can be either positive or negative. The only numbers that can be on bottom is 1 and negative 1. So let's make a list of possible rational roots. All right? So what I'm going to do is I'm going to take each one of these numbers on top and put it over the bottom one. So when you put 1 over 1 and reduce it, what do you get? 1. So we could either have positive or negative 1. Now I want to take the 3 and put it over all the bottom numbers. So 3 over 1 reduces down to just 3. All right? So we have 4 possible rational roots. Now I want to know which one works. It says find all the rational roots. Okay, what did I do? I just generated a list of possible rational roots. I want to find them all. So here's what I'm going to do. To find them all, I want to use synthetic division. Okay, so I'm going to test each one of these. Remember, when you use synthetic division, you just list out the coefficients of your polynomial equation here. So I'm just going to list out the coefficients here. Make sure none of your x's are skipped over. We got to the third power, to the second power, to the first power, to the 0 power. So none are skipped over. So our coefficients are 1, 1, negative 3, and negative 3. So let's test out 1 first. Let's see if 1 works. So let's test positive 1. So I'm going to drop this down under the line. Take 1 times 1, which is 1. Add these together. 1 plus 1 is 2. 1 times 2 is 2. Write it up here. Negative 3 plus 2 is negative 1. 1 times negative 1 is negative 1. We get negative 4. So the remainder is negative 4. Well, I know that's not a root of it, because to be a root of it, the remainder should be 0. So I can eliminate 1. 1's not going to work. All right? So let's test negative 1 next. So let's try 1, 1, negative 3, negative 3. We want to test negative 1. Let's see if negative 1 works. So let's plug negative 1 and use synthetic division. So let's drop the 1 down. Take negative 1 times 1 is negative 1. 1 plus negative 1 is 0. Negative 1 times 0 is 0. Negative 3 plus 0 is negative 3. negative 1 times negative 3 is going to be positive 3. And then last, negative 3 plus 3 is 0. This one works. So we found one of the rational roots. One of the rational roots is negative 1. But we still got two other ones we want to test. Because this is degree 3, it could have 3 possible rational roots. Because it has 3 roots. We just don't know what type of root it has. But we know one type it has. One of the roots is negative 1. That's one of the rational roots. Does it have any more rational roots? Well, if it does, the only other 2 numbers that could be rational roots of it are 3 and negative 3. So let's test out 3. Let's do it the same way with the other ones. So let's use synthetic division. Let's see if 3 works. So bring the 1 down under the line. 3 times 1 is 3. 1 plus 3 is 4. 3 times 4 is 12. Negative 3 plus 12 is 9. 3 times 9 is 27. We'll get 24. Since the remainder is not 0, we know 3 is not a rational root. And then we just got to test negative 3. There's one more we need to test. Let's test negative 3. Again, we're just using synthetic division. So bring the 1 down. Negative 3 times 1 is negative 3. 1 plus negative 3 is negative 2. Negative 3 times negative 2 is positive 6. Negative 3 plus 6 is 3. Negative 3 times 3 is 9. We get 6. The remainder is 6. So that means negative 3 is not a rational root. So we concluded this. We came up with a list of possible rational roots by using the remainder theorem. By looking at factors of my constant term over factors of your leading coefficient. We've generated this list. So we had 4 possible rational roots. 1, negative 1, 3, negative 3. And of these 4 possible rational roots, only one of them worked. So what that tells us is this. That equation has 1 rational root. Which is negative 1. But it was a cubic equation, so it has 2 other roots. We just don't know what type of those are. It still has 2 more roots. The roots could be complex or imaginary, or it could be irrational. We're going to save that for a different day, how to find the other 2 roots. Today, we'll just focus on the rational roots. All right? So this is a little confusing, so I want to look at one more example here. All right. So this example asks you to find all the roots. We're not going to do that. We're going to finish this example tomorrow, but we're going to start it today. So what I want you to be able to do today is I want you to be able to generate that list of possible rational roots. Okay? So I want to be able to do that. So if we remember, if it's a rational root, we can write in the form P over Q, where P is factors of what? Factors of your constant term. So my constant term in this equation is negative 1. So P can be factors of negative 1. And then on the bottom, we're going to look at factors of my leading coefficient. What's my leading coefficient on this equation? 2. All right, so let's write out all the factors of 1. Well, we got 1 and negative 1. These are all the factors of 1. What are all the factors of 2? Well, we got 1 and negative 1, and 2 and negative 2. So I want to generate this list. I'm going to call it, this is my list of possible rational roots. So we're just going to call it PRR. Possible rational roots. So here's what we're gonna do. We're gonna take all the numbers in my numerator, which is positive and negative 1, and put them over all the bottom numbers. So we're gonna put 1 over 1 and then reduce. 1 over 1 reduces down to just 1. So we got positive, negative 1. Now I'm gonna take 1, my positive and negative 1 on top, and put it over positive, negative 2, and then reduce. So 1 over 2 reduces down to 1/2. So here's my list of possible rational roots. They could either be 1 or negative 1, or 1/2 or negative 1/2. This is my list of possible rational roots. I don't know which one works until I test them. And to test them, I would use synthetic division.